Again, we'll just look at it in a larger size. Also, you can see that there's just, I saved all the intermediate files. You don't have to do that, but just so you can see that there was all the different ones that started. And then there it is. So again, it's a degraded image, but that is an image. It's a no-op slide now, except for on the right-hand side, you can see there's some stripes. You can let it go, and then just stop it once it gets zoomed in further. And so you can see down the right-hand side, there's a series of stripes there, and that's our shellcode. And the reason they show up as stripes is that every line is the same shellcode. So it doesn't matter where in the image that it lands, it's still going to hit the same, no matter what row it lands on, it'll still hit your shellcode. Like in the BlackHat logo example that Greg had, he just used one line because he wanted to hide it. And this is obviously less stealth by doing the whole thing, but easy to hit. And this is just a proof of concept. I mean, does that actually work? Is that a no-op sled? That shellcode is pulled straight from Metasploit, launches calc.exe. Does it really work? Yes, it does, but I'll save that for Greg's demo because he does the same thing, but he does it with a PNG file.
Yeah, JPEG files are not ideal for storing shellcode. They're developed by the Joint Photographics Expert Group for compressing photographs, which tend to have smooth edges and a lot of low contrast features, like where nothing changes too much over space. They're not appropriate for images with sharp lines and high contrast areas, like line graphs, cartoon images, or any image with fine details, and shellcodes of fine detail. The challenge is basically the lossy compression results in the loss of information, which definitely damages the instructions. It can be non-localized damage, just due to the way the compression algorithm works. The available instructions can depend on instructions which are several bytes away or several lines away, which can be several tens of K away in memory. One of the solutions we tried for this were carefully hand-coding the entire shellcode so it would decode properly in a JPEG, which was very hard, and Windows shellcode's huge. The second method was to make a shellcode decoder stub and use that to extract the main shellcode and execute that. That's a technique which is used by a lot of other encoding methods, and I got that to work with some toy images. But if you change the stuff too much, it breaks again. You needed to have a lot of clear area around it. But then I tried to be a little bit smarter about it. Actually learning how JPEGs work before trying to abuse them helped a lot. A JPEG is how it gets encoded. Basically, it typically gets stored in YCBCR format, color space. The Y is the brightness, and that's the most visually important part. And the CR and the CB, that's the complement of red and the complement of blue. And it tends to drop information out of those to increase compression because your eye doesn't see so much in the colors. So basically, after you've broken them apart into the color components apart, you break each of those images into a series of 8x8 pixel blocks. Then, on each of those blocks, you apply what's called the discrete cosine transform, and then you do what's called quantizing the results. And you end up with a list, which is then Huffman encoded, which basically gives you the compression some of the compression that JPEG does. Then you add the required headers and the Huffman encoding tables, and you've got your JPEG. The DCT provides a list of values which tell you the amount each frequency contributes to the image. It basically breaks it from being basically breaks the space it's in from being the position into the frequency space. That formula there is kind of complicated. I have a picture an animation I think, which demonstrates it if I can find the mouse cursor. It's on the top left is the picture it's aiming for. In the top left corner of that thing is the picture as it's got to so far. the parts that it's made of, as it's moving along, you see this is where it's actually up to in the bottom part of the image, which is the table of coefficients for that particular block. And the pattern that's moving in the with the stripes and going in each direction is the basis function for the discrete cosine transform that it's producing at the moment. And the black image in there is the difference. How it compresses it is it takes the coefficients from that bottom thing and divides them by the quantization factor, which is just a number which has been chosen pretty arbitrarily. And if it becomes 0, it's much easier to compress. The reason it's going in a zigzag is because the top part of the image, the top part of the black and white checkerboard stuff, is more important. And you will tend to get more zeros in the rest of on the rest of it, where it comes to later in the zigzag pattern. Yeah, to get it back, you just multiply by the. Yeah, okay, this is getting technical. But JPEGs tend to break shellcode because the DCT part and mangles stuff, even if you're at the highest quality setting. If you look at the left thing there, that's the original code, and after you JPEG mangle it, you end up with what you got on the right, which isn't at all what you asked for. So trying to run that, it will just crash. There's certain instructions which you can encode at certain positions without them ever being changed. So aligning where you put it is important. Maximizing the JPEG quality definitely does limit the amount of loss, but it makes big images. You can actually improve the compression though by scaling up by a multiple of 8 in each direction over just some other random value, just because it works on 8 by 8 squares. We did write a decoder stub which is JPEG safe, as I mentioned before, but it's not very useful at all, and it was just for proof of concept. There's a lot better way of doing it. If you use the right color space, a good quantization table, and you store it in the right shape, shellcode can be inserted without it being modified. As I said, the JFIF file, which is a JPEG format information file, image file, uses the YCBCR, which covers a different range of colors than RGB, which is what everything will get converted to when it's displayed on your computer. The color space is lossy. It will tend to lose the least significant couple of bits from many of the bytes. And there are colors which can't be converted due to the way the format works. Like a 16.8 million color image, which covered all of the colors available for 24-bit. After I converted it into the YCBCR space and then back into the RGB space, only at 2.6 million colors. So that's about 1/8 of the colors disappeared. They're outside the color gamut for that. But you can sometimes, depending on the tools you use, encode your JPEGs with RGB color space. And you have to have the right shape. If you scale as I said, scaling the image to some multiple of 8 by 8 times its current size, until it's big enough to fit in memory, do that. JPEGs, they work on those blocks. If you don't use smoothing, the compression gets helped. I think I mentioned that already. The image here, you can now decode that entire block with only one DCT coefficient per block. If you look at how the basis function in the top, if you remember the top left-hand corner of it, it was all one shade. It's because it encodes the average color and none of the frequency components. So if it's just a single square, it's just going to be one value set, and the rest of the coefficients are going to be 0. So, and then if you choose where to put the shellcode with Internet Explorer, if you put it in the top right, then you got the whole image to go through as an OPS LED. It does it from bottom to top rather than top to bottom like other programs do, and I don't know why. And then you saw 8 copies of it, one on top of the other. Yeah, okay. Why do we want to stack 8 copies of the shellcode? Well, because it works. That's the short answer. Here's the longer answer. Basically, it's for the same reason as you can do as encoding it with just 1 byte from as while you break it into 8 by 8 for the and you can encode it with just one DCT basis function coefficient. A constant value degenerates to the case where the average value is the only one you need. However, with this, each two-dimensional DCT basis function is actually the product of two one-dimensional basis functions. You can, the horizontal component and the vertical component. If you don't actually have a horizontal component, it just becomes 0. So if you have a series of stripes, which, let's see, where's it? Should I change the mouse color? Series of stripes like this. You can see that the coefficients on the bottom square where it's moving the dots along, it's only on the top row where the values are stored. That means we only have to store 8 values instead of all 64 values to store the stripes, which means we can, it has less chance for making a mistake. Okay, yeah, I'll make that a bit easier. The A block, basically, if you've got less stuff to add up, there's less chance of it making a mistake. That's basically what the stuff at the bottom says. It's, yeah, a little technical, sorry, so here's a demo. This is the output of my one. It doesn't quite look as pretty as Michael's, but what I did was download a file, just a random one off the web, ran the script over it, which is what JPEGs-POC, the actual program you run, is called, and copied that to var temp. So you see the output of it, very pretty, tells you what's going on at every step along the way. It automatically picks a good scaling size for you that takes up a certain amount of memory. And yeah, you end up with a 3 meg JPEG, which actually compresses quite well with if you use mod gzip. So as I run it, first we load it up in IE, and yeah, it takes a little while to load. It's the quality on this, some of it's due to the AVI and some of it's due to the image itself. Then open up Ollie. Because we haven't used any exploit, I've used Ollie debug to actually run the code. So I'm just going to move the EIP to the right place in there. So we select that, open it, wait for it to load. Yep, and then we start it running again so we can get rid of the debug thread, make sure it's still there. Yep. So yeah, the colors, yeah, the flowers look nice. So. Okay, and then we have a look at the memory map, sort by size, and our one's right at the top because it's the biggest one. The amount of space that takes up is about 175 meg. So that's a huge target for us to aim for. So I just copy the address, and we'll have a look at that in the data. And yeah, that's the code we want, and it takes up a large amount of space, like from OX20, I think it was around OX200020 to a big amount, so add 175 to that. We don't actually get to see my shellcode because I didn't scroll down far enough because it wouldn't fit on the screen because I resized it. So yeah, it takes a huge amount of space up, and I couldn't be able to scroll all the way to the bottom. Over here, if we go to that address, and see, I've done it before. There we go. That's the actual code it's going to execute in there. So those instructions, like the rest of the instructions that follow up for the next 175 minus the size of the shellcode length, are all don't do anything.